Okay, advanced science. We are gonna start off our advanced science biology course with some basic chemistry. This is gonna come up quite a lot when we're thinking about proteins, and it's gonna be really important that we can go back to these basic principles and think about them. What I'm going to try and do is, probably not very neatly, is try and get the basics of what we're talking about onto this A4 bit of paper so that we can come back to it and we can use it to talk about the interactions our proteins will eventually go on to have. So we are going to start off with some really basic principles, and we are going to finish off hopefully with an understanding of a polar covalent bond. And even if you haven't done much chemistry in the past, this should be a fairly basic way of us getting started with things. So we are going to start off with the very basic principle that we have things with charge. And if things that have a charge are the same, so if we have two positive charges, those two positive charges will want to repel each other and move away from one another. So if you've got two positive charges sitting quite close together, they are going to want to move apart from one another. Now, if the charges are negative, they are also going to want to move away from one another. So if you've got two negative charges, they are going to want to move away from one another. Now, you could have a situation where you've got a positive and a negative charge. In that instance, those charges are going to want to move towards each other. Now, from this very basic principle, we're going to start to build our atom and our first element. So we are going to start with the first element on the periodic table, which is hydrogen, and we're going to have a nuclide notation with a mass number here. So this is our mass number, and that is our protons, which are our positive charges, and our neutrons, which don't have a charge. So there is no charge at all there. This number here is our atomic number, and that is just the number of protons that we have. Now, there are different ways to view and to visualize an atom. There are lots and lots of really interesting physics and deep chemistry about the atom, which we won't be going into. What I want you to focus on is thinking about these positive and negative charges and using the straightforward visualization that we'll be building up. So, if we've got an atomic number of 1, that means we only have 1 proton in our nucleus, and we may have 1 electron on the outside if we have no charge. So if we have no charge, then we've got to have a positive and a negative. -1 plus 1 is 0. So this is our atom. It has no charge, and because it's got 1 proton, we call it hydrogen. And our electron is in an orbit around that nucleus. You can view the atom like a solid sphere. That isn't going to hinder you in any way, shape, or form. But we're gonna try and view it like this for the time being. Now, what we can do with this atom is that we can add it to another atom and form a molecule. Now, this happens because the molecule is actually more stable than the other two atoms when they're on their own. So what we're going to do is we are going to have 1 hydrogen over here, and it's going to have its 1 electron here. Then we're going to have another hydrogen, hopefully about the same distance apart. They look about the right distance apart, and they are sharing their electrons. That forms a covalent bond, and that is more stable than having two hydrogen atoms on their own. So this structure, we can put a little sphere around. They should probably be nice big circles, but I'm not going to worry myself with that. What I really want to focus on is the fact that these electrons are exactly halfway between the two hydrogens. Now, if we look back to our little chart, we know that positive charges want to move towards negative charges, and negative charges want to move towards positive charges. The electron doesn't ever fall into the nucleus as far as we think about it. There's a couple of interesting physics things, like the Heisenberg uncertainty principle, and the fact that these electrons are more like a wave function than they are an actual particle, but we're not going to go into any of that. And if you do the advanced higher chemistry course, you'll actually talk a little bit about how these electrons present themselves as different orbits, like the s, p, d, and f orbitals. But for the time being, and for the moment, what we want to be thinking about is we've got a 1 positive charge over here, and we've got 1 positive charge over here, and we've got our 2 negative charges right in the middle. Now, that positive charge there is the same as that positive charge there. So in this tug of war, those 2 negative charges stay right in the middle. Now, what would happen if I added another positive charge over here? Well, we've got more positive here than we do here. So that's going to make our electrons move to that side. Now, this all comes down to electronegativity. Now, hydrogen has an electronegativity of 2.2, and this one has an electronegativity of 2.2. And you can think of this like strength at pulling electrons towards the nucleus. Because they're the same, the electrons sit in the middle. Because I've added a proton here, or a positive charge here, I'm going to shift. I'm going to give this side more of this electronegative strength, and it's going to want to pull those electrons closer to that side. So, if we build a molecule, let's say we've got hydrogen, which has an electronegativity of 2.2, and we've got an atom of fluorine, that atom of fluorine has an electronegativity of 4. Now, if we're going to place our electrons in this molecule, are they going to be closer to the hydrogen or the fluorine, or are they going to be right in the middle? Well, this fluorine has more electronegativity. It's higher on the Pauling scale, and so the electrons are going to want to sit more to this side of the molecule. So I'm going to do my electrons sitting here, like that. And what I'm going to do is I'm going to visualize this a little bit like this. So this is going to be what my molecule looks like. And forgive the terrible art. This is our molecule here. And the electrons are sitting over this side. So this side of the molecule, because the electrons, in fact I'll do, this is the midpoint of our molecule. So this side here is going to be slightly negative. Now that's the Greek sign for delta. It's what we use for slightly negatively charged. This side is going to be slightly positively charged. It's not what we would term a full charge. So it's not like we've got one more electron on this side or one more proton on this side. It's just slightly negatively charged because these electrons are further over to the fluorine. In fact, because fluorine's so good at pulling electrons, this would create a situation where you would end up forming hydrogen bonds, and this molecule would be really quite polar in its characteristic. So this molecule here would be non-polar, so non-polar, because the electronegativity of the two hydrogen atoms is the same. The electrons are shared equally in the center. This one would be polar, and we have formed the same type of bond, so it's a covalent bond, the share of electrons, and we've got our hydrogen here, which is just not quite as good at pulling electrons towards it as the fluorine is. Right, what we're going to look at next is the periodic table, and we're going to talk a little bit about bonding in the periodic table and how the periodic table functions. Okay, so what we're going to take a look at now that we have spoken a little bit about how we get a covalent bond and how we form a molecule is the molecules that we're actually going to be seeing in our amino acids and eventually our fully formed proteins. So the elements that we really want to be taking a look at here are hydrogen, carbon, nitrogen, phosphorus, sulfur, and oxygen. So this block of elements is really all that we're going to be focusing on for the first little bit. There are quite a few other elements that we find in the human body, and we will be taking a look at ions like the sodium and potassium ions and how those ion pumps work in active transport. In terms of the rest of the periodic table, there's really a lot of interesting elements that have biological functions. We might well be at some stage taking a look at the inhibition of enzymes in conditions where there's high levels of lead. We will probably be speaking about DNA in the context of it having a magnesium ligand. This is actually really interesting because depending on what our ions are like, so if our ion is very similar in size to another ion, like aluminium, there can be some problems that we get when these ions are swapped with each other in DNA. In terms of the transition metals, really iron is going to be the big obvious one, and we'll be talking about that in the context of hemoglobin, and we'll probably be using hemoglobin with our protein visualizer program later on. I think we're going to try and use PyMol to do some of that, and hopefully I'll be able to take you through some of that this lesson as well. Right, the next little bit that we need to look at is a fully formed amino acid, and so we are going to be playing about with our hydrogen, our carbon, our nitrogen, and our oxygen mainly. We will come on to the phosphorus and sulfur later on when we start talking about some of the more complicated amino acids, and we'll talk a little bit more about that. So, on to the next little bit. So, from the periodic table, we highlighted a few elements that we might be quite interested in. Those elements that we're really interested in for the time being are just going to be hydrogen with a mass number of 1 and an atomic number of 1. We also have carbon with a mass number of 12 and an atomic number of 6. We have got nitrogen with a mass number of 14 and an atomic number of 7. And finally, the last one of our elements that we need to play about with is oxygen with a mass number of 16 and an atomic number of 8. Now, what we're going to do is we're going to build a very basic amino acid, and we're going to talk about the structure that's in common with all amino acids, which is really the backbone structure that will link our amino acids together eventually. Now, what we need to cover a little bit is the valency of each of our elements. So hydrogen can make one bond. So the valency of hydrogen is just 1. Carbon is 4, and that's really why carbon is so important in biology and in how it forms molecules, because it, along with silicon, are really the only elements that form 4 bonds easily like that. And silicon still doesn't have quite some of the same properties as carbon. It's why we tend to say life is carbon based. Nitrogen has 3 bonds that it can form, and oxygen has a valency of 2. So when we are thinking about our structures, we're going to think in terms of how many bonds each of these can make. We spoke a little bit about the electronegativity. We will talk a little bit about that later on, but for the time being, we're just gonna build our very basic structure. So our first bit that we've really got to talk about is the name itself. So our name that we've got is amino acid. And this actually tells us a fair amount about this molecule. It basically tells us that we've got an amino group, which is just an N with 2 hydrogens. So a nitrogen attached to 2 hydrogens is our amino group. And what that nitrogen is attached to is a carbon. Now that carbon is going to have the R group. This is actually what we're really going to be interested in later on once we've done all the fundamentals. Coming off that carbon, we've got another hydrogen, and that carbon is attached to our acid group. So our amino group is here, and our acid group is here. Now the acid component to this is a carboxylic group, or a carboxyl group. That is found in things like vinegar, and it is just a carbon with a double bond to an oxygen, and another bond to another oxygen atom, and that oxygen atom has a hydrogen at the end of it. Now, if that hydrogen was to dissociate, so come away from that oxygen, you'd be left with an O negative and an H positive, and that H positive would be your acid component. But we're not going to go into that in too much detail. We're actually going to leave it for now, and we're going to talk about this structure here. Now, this is actually a 3-dimensional structure, and we can show this with molymods. So my molymod here has my double bonded oxygen and my OH here, and we've got my little nitrogen here and 2 hydrogens attached there for the amino group. That silver bit there that doesn't have anything attached to it, that's our R group, and this can represent a lot of different things, and we're going to take a little bit of a look at what this R component can be. You can just refer to it as rest of molecule for the time being. So this is our single amino acid, and we're going to have to build a chain of these to form a polypeptide, and then we're going to have these R groups interact within that polypeptide to form our secondary structure, and that will go on to eventually form our quaternary protein, but it'll be a fair few videos until we actually get to that stage. So R group, this can be anything. These things are fixed. This is what you find in an amino acid. Now, as I've got this sitting here like this, I can bring in another amino acid, and what we're going to do is we are going to have the amino group coming quite close to the acid group, and what's going to happen is this oxygen is going to pop off. Now, we don't actually really want just an OH moving about. That OH is going to attach to one of the hydrogens from the amino group. So we are going to form a water molecule, and that water molecule is going to go away from here, and it will just become one of the octillions of other oxygen molecules in your water molecules in your body. Now, this leaves us with an interesting situation. This carbon wants to have 4 bonds, and it's got 1, 2, 3 currently. So this 4th bond is open to forming. There's an electron here that's open to forming another bond, and that is true with the nitrogen on this side as well. So this is going to form together, and here we've actually got our peptide bond. So we've got a carbon with a double bonded oxygen bound to a nitrogen with a hydrogen attached, and then we've got the other amino acid off this side. Now these together, this is our first amino acid up to here, and this is our second amino acid that we've joined onto here. Now we could keep going with that. So as you can see, this second amino acid actually has our acid group at the end, and we could take this off and form it up again, and we would keep doing that until we've got this long polymer. Now the R groups that are here, these could be the same, they could be different, and we will go into how these R groups, what they look like next. So that there, if we take a little bit of a minute to go through carefully what's just happened. We had a nitrogen with our hydrogens bonded to it there, and we had that nitrogen attached to another carbon with another R group, could be the same as this one, could be different, and we've got our acid group, which is our carboxyl group, and we've got our hydrogen there and our last hydrogen here. So as I showed you with the Molymods, it's actually this area here that is lost. So we lose that OH and that H there to form H2O, and then we form a covalent bond between that carbon and that nitrogen. And that bond there, it is just a normal covalent bond, but because we speak about it so much, that is our peptide bond. Now, the next thing that we are going to do is we're going to take a little bit of a look at all the different R groups that we find in amino acids and talk a little bit about that. Okay, so what we just spoke about was our amino acids and how they can form bonds, and we really want to talk about the R groups for each of these. Now, there are 20 amino acids that the body uses directly to make proteins. There are a lot more amino acids than that, but these are the ones that we really want to focus on. And probably for the time being, most importantly, what we want to do is highlight the ones that are either hydrophobic or hydrophilic, and we'll explain in the next bit why that's important. So alanine has our amino group there, our central carbons there, and out here is our R group. Now that R group in this case is a CH3, and that would be a non-polar group. So what I'm going to do is, just for the ones that are hydrophobic, I'm just going to put a little gold dot there. And this is going to be important, and we'll come back to this. Glycine's actually our most basic amino acid, and our R group is actually just a hydrogen coming off of here, and so this one is pretty hydrophobic as well. Isoleucine and leucine, once again, they have an extended hydrocarbon R group, so their R group is just hydrogens and carbons. So once again, this is going to be quite hydrophobic, and this one too. Now we're going to skip a few of them because we don't really need to talk about all of them too much in detail, but what I'm going to do is highlight a couple of them that are either quite polar or actually have a formal charge associated with them. So what we're going to do is we are going to change the color here, and we are going to go for a dark blue. And this one here, aspartic acid, has a negative charge. Now that means that this molecule will, at least that portion of the molecule will be attracted to other positive charges, and it will be repelled by negative charges. And the fact that it is charged will also mean that it is hydrophilic, so it will want to associate with other things that have a charge. And like I said, we'll go into this hydrophobic and hydrophilic thing in just a second. Glutamic acid, just beside it, is again, that is very hydrophilic, and it's got a negative charge there as well. Now arginine and histidine, they have this part here has got quite a lot of polarity, but it's not a formal positive charge. But there is, this part of the molecule here would be quite polar. So this bit here would be relatively polar, and we're told that it's also basic, which means that it's associated with alkali environments, and it will produce alkali environments. The same can be said for arginine. Now these really are all our different amino acids, and for example, if you were to pick a few of them, so if we were to say that a part of the DNA said that we wanted alanine, followed by isoleucine, followed by leucine, well, we'd actually produce a section of that protein that was fairly hydrophobic. There's not much there with any charge, and so that section would not want to associate with things like water that is polar. It would want to associate with non-polar things, and that would give a very specific functionality to that part of the protein. Then as we move through the protein, we might have aspartic acid and glutamic acid linked together, and because these are negatively charged, that might cause that part of the protein to conform in a very specific way that's part of the functionality for the protein overall. Now, you are never gonna have to look at a bunch of ticks and say whether or not that protein would conform in a specific way or something would happen with it specifically. What you would have to do is make some general comments about that. So in the next part, we'll go over the hydrophobic and hydrophilic, and when we do that, I want you to be thinking a little bit about the amino acids that we've seen here. We don't need to go into a huge amount of detail. You don't really need to know the names of them. It's probably a good idea that you get to grips with some of the basic names, like glycine's your simplest one. You might want to pick out arginine as one with a formal positive charge and aspartic acid as one with a formal negative charge, just so you've got something in your head to really think about. And just to highlight, before we move on with our sulfur, our methionine has a sulfur atom in it, and we will be talking a little bit about how sulfur makes a bit of a difference with its electronegativity as well. Got a sulfur there. We will talk a little bit about disulfide bridges, so it's maybe a good idea to bear these ones in mind as having sulfur in them. Okay, so the last little bit that we've got to deal with now that we've looked at our different amino acids is what is going to happen, because we've got some R groups that are polar, aka they've got some kind of a charge, and those that are non-polar. And what I want to do is just look at how polar molecules and non-polar molecules interact, and then we'll actually do a highly exciting experiment at the end, and that'll wrap us up really for the introduction to the chemistry bit of the topic. So what I want to do is I want to show you first a water molecule which has this angular structure here. Now, as we spoke about before, there's different electronegativities for each element, and the electronegativity for oxygen is 3.5 on the Pauling scale, which means it's got a fairly high pool for electrons. As we discussed earlier, hydrogen has got a electronegativity of 2.2. Now, this means that the electrons will be getting pulled in this direction, so that this part of the molecule will have a slight negative charge, while both hydrogens have a slight positive charge. So this molecule here is polar, and water is going to be by far and away the most common molecule within our cells. And so it's going to be really important that we speak about this in terms of water a lot of the time. So what do we have if we've got a non-polar substance? Well, we are going to be focusing on hydrocarbon chains, and these are pretty good non-polar molecules. So if I put in a hydrocarbon, just like methane, there's really two things going on here that mean that it's non-polar. The electronegativity for hydrogen is 2.2, and for carbon it's 2.5. So these aren't really that much different. However, carbon is going to have slightly more pool than the hydrogen. However, this is compensated by the fact that the molecule itself is symmetrical. So wherever you've got any additional pool, the other side of the molecule is going to compensate for that. Meaning overall, this molecule is going to be non-polar. Now, when we talk about something being hydrophilic or hydrophobic, what we're really saying is a molecule that's polar is going to be hydrophilic. And that just means it's going to want to interact with water. When we talk about something that's non-polar, that is going to be hydrophobic, and it isn't going to want to interact with the water. Now, we've kind of got to explain this a little bit better than just that. Really, the non-polar substances are going to be excluded by the water, and I can hopefully display this using our methane that's here and a few water molecules like this, and then I'm going to show you what happens in real life. So these water molecules, the oxygens are not going to want to come together. Hopefully you can remember that if it's negatively charged, then they're going to want to push each other apart. However, the hydrogen component of the water molecule is going to be attracted to that slightly negatively charged oxygen atom at the end there. And what we're going to get is we're going to get these water molecules are going to want to interact with each other's slightly different charged portions like that. Now, the methane molecule is going to be excluded. So it's either going to form a single bubble in the middle, or these water molecules will come together slightly more closely to exclude the methane. In essence, what we're saying is the methane molecules are not going to be equally distributed throughout the water like that. They're going to be pushed together because the water molecules are going to want to be interacting with each other in this fashion. So our methane molecules are going to be excluded from the water, so they don't want to interact with the water, and they're going to be forced together. Now we can show this. We can show this pretty straightforwardly with a little bit of water and some oil. Now the oil, once we get enough, hopefully you can see, is not mixing with the water in any significant fashion. It has created what is essentially an island in and of itself. If we move that island to the side, if we can, we can't, which is good, but we've got, there we go. Those water molecules are surrounding the oil droplet, and this part here is all of our non-polar molecules, and they're hydrophobic, which means they don't want to interact with the water, but they will interact with themselves. So what we've got with that oil is essentially a fat molecule. So we have got, and I'll keep it over this side, we've got some carbons with some hydrogens, like this. Now, in essence, this entire portion here, the biggest chunk, the fatty acid portion of this, is almost entirely non-polar. So that's really the section that doesn't want to interact with the water at all. If we've got any interaction at all with the water, it's going to be created by this little bit here. So if we had an electron microscope, what we might be able to see is the fatty acid chains being forced into the center of our little bubble of oil that we've got here. So all in all, that is the part that we want to be talking about with our R groups in our amino acids, whether or not they're polar and they will want to interact with the water portion of the cell, or if they're non-polar and they'll want to interact in a different way with the water within the cell. This will also have an impact on how they take up their conformations eventually in their fully folded structure. Hopefully the link between the polar and non-polar amino acids is at least a little bit clearer at the moment. So if it's polar, it's going to want to interact with water. If it's non-polar, it's going to want to find a portion of the cell that is also non-polar, and that's actually going to be in between our membrane, but we'll get onto that a little bit later. Really, this was what I wanted you to kind of understand, is that the water will exclude non-polar molecules, and they won't be able to mix together, and you'll get this isolation of our non-polar molecule. Right, what I'm going to do is we are going to finish off there with the chemistry, the starter chemistry stuff for the advanced higher biology. What I'd like to do is do a Q&A, so I will do another video after this one answering any questions that you've got on what we've tried to cover. I understand this is definitely the first time for me trying to teach like this, and honestly the way in which it's been set out has maybe been a little bit difficult. Hopefully we've grasped some of the basics, and really it's probably a good idea that you go through the video and pick out the key points and make a list of them. When we do the Q&A, what I'll do is we will start off with what I really wanted you to pick up, and we'll go through any questions that you've got. Good luck!